We'll move on now to solving linear differential equations using something called integrating factors. And to introduce those, let's look at this warm-up exercise. Given two functions of t, y is a function of t and mu is a function of t, calculate the derivative d dt of mu times y. This is just asking us for the product rule. So we'll have mu prime y plus mu y prime. In what we're going to be doing, though, we're going to have those terms in the opposite order, which is the same thing. To solve linear differential equations, we will need to be able to recognize when we're dealing with the answer to the above calculation. In other words, when we're dealing with something of this form, because what we're going to want to do is then understand that we can bring it back to that. So the reverse of the way we're used to doing the product rule. So to get a little feel for that, let's see a couple of examples. Referring to the warm-up exercise, what would mu be in e to the 2t y prime plus 2e to the 2t y? Well, notice mu is the thing multiplying the y prime. That's where mu ended up when we differentiated. So mu would have to be e to the 2t. So what product would we differentiate to obtain e to the 2ty prime plus 2e to the 2ty? It would be mu y. In other words, e to the 2t times y. Let's check and make sure that we're actually right about that. Let's actually differentiate e to the 2ty. So differentiating e to the 2t, I have 2e to the 2ty plus, and next I keep the e to the 2t and differentiate the y. And that is the same thing as saying I have e to the 2t y prime plus 2e to the 2t y. So indeed, this function, if you differentiate it, will give you that expression. With all that in mind, let's evaluate the indefinite integral of our expression. We've already determined that our expression is the derivative of e to the 2ty. So we have e to the 2ty. We first differentiate it and then we integrate it. What happens if you differentiate and integrate? You get back to where you started. Remember, differentiation and integration cancel each other out. So we wind up with e to the 2ty. Let's try this again for cosine of t squared y prime minus 2t sine of t squared y. What would mu be? Mu would be the thing multiplying the y prime, so that's cosine of t squared. What product would we differentiate to obtain this expression? Mu y, in other words, cosine of t squared times y. Let's check to make sure we've got the right product. And I'm going to go ahead and do the differentiation in the order that we want to see it in. So I'll differentiate the cosine of t squared second. So that's going to give us minus sine of t squared. And the chain rule says we have a 2t. And then we're going to keep the y. And I'll do the step that's usually the second term. I'll put that in the first spot. So in the first spot, we're keeping the cosine of t squared, and differentiating the y. So we get cosine of t squared y prime minus 2t sine of t squared y. If we now want to evaluate the indefinite integral of our expression, it's a piece of cake because we already know that our expression is the derivative of cosine of t squared y. So if we take that expression, differentiate it, and then integrate it, we get back to that same expression. To solve a linear equation, so one of the form y prime plus p of ty equals g of t, we're going to multiply both sides of the equation by something we call mu. That's why I was calling that other function mu on the previous page. Mu is defined to be e to the integral of p of t dt. So we multiply both sides by that, and then we integrate. And this function mu is called an integrating factor. Because it allows you to actually integrate, something that you might not have been able to integrate otherwise. In the next video, we'll see step by step in an example how to compute and use this integrating factor to solve a linear DE.